No worries. Yeah, all right. We're going live now.
You're live now. You miss recording.
Welcome everyone to the Direfuse webinar series. We'll get started shortly. Before we begin, these are a few introductory slides that we run like every time. We have these webinars recorded and archived, so anytime you can go back and view these webinars at our website. The webinars has a dedicated page where all of these, the past 6 webinars have been uploaded. The 7th webinar that was on desalination in the coastal bend region is yet to be uploaded. So please bear with us as we work through our schedules to upload that to the website. We also had our Texas workshop last year, which is now available as the workshop's panel discussion is now available on the website on the landing page. So I strongly encourage you to visit that. We also have had a very special webinar and a seminar from our Indian partners, WWF India and our Observer Research Foundation. Dr. Anurag Danda visited us in November, and his webinar has been recorded on coastal resilience and archived in our webinar page as well as a special webinar. So all of this information is available to you in on the website for Direfuse. We strongly encourage you, if you're joining us for the first time, we strongly encourage you to subscribe on our subscription page. You can find a link to this on the landing page for the website, and you can subscribe updates and information on webinars such as this one, as well as information on any workshops that are upcoming. So with that, I will turn it over to Basil Daher. Dr. Basil Daher is with Texas A&M Energy Institute to introduce today's webinar. Basil, over to you.
Thank you very much, Dabelina, and good morning, good afternoon, everyone, wherever you're joining us today, and welcome to our 8th webinar of the series of the Direfuse project, which is about disaster resilient food, energy, and water systems. Again, this is part of a planning grant as part of the Sustainable Regional Systems Research Network by NSF, which aims to build a convergent research program, which will develop a new class of multifaceted resilient systems to urban connected communities and sustainably managing food, energy, and water systems. Today's session will focus on food, energy, water nexus with perspectives and methods to facilitate systems analysis. Water, energy, and food security challenges are global challenges that are complex and that are tightly interconnected. And with a growing population that is expected to hit more than 10 billion by 2050, with growing shocks to these interconnected systems, it's more urgent than ever that we understand these interconnections and better develop the tools and the analytics so that we can guide evidence-based decision-making toward better, sustainable, and resilient systems. So we have a great lineup of speakers today with a wealth of experience and knowledge to share on this topic. We will have 3 speakers. We'll have 20 minutes each for short presentations by each, followed by a half-an-hour engagement session with our speakers. So I'd like to ask you to share your questions in the chat box as you listen to the presentations, and we're going to have that Q&A toward the end of the session for the second part. So with that, it gives me great pleasure to introduce our first speaker for our webinar today, Professor Rabia Mahtar. a longtime mentor, colleague, and friend, and it gives me great pleasure to introduce him. Professor Rabia Muhtar is a professor in the Department of Biological and Agricultural Engineering department, as well as the Zachary Department of Civil and Environmental Engineering at Texas A&M University. Dr. Muhtar's research focuses on global resource challenges and the development of water energy food nexus framework for linking science and policy, as well as the characterization of soil water medium using thermodynamic modeling and the efficacy of non-traditional water, including applications of sustainable integrated water management with a focus on implementing the Sustainable Development Goals. Professor Muhtar serves as the governor of the World Water Council and as vice president of the governance committee of the International Water Resources Association. He is a distinguished alumnus of the American University of Beirut, as well as a senior fellow at the Policy Center for the New South and the fellow of the American Society of Agricultural and Biological Engineers. Professor Muhtar founded the Texas A&M Water Energy Initiative at Texas A&M in 2015 and served as Dean of Faculty of Agriculture and Food Sciences between 2018 and 2021, where he also founded a Water Nexus initiative there as well. With that, I'll give the floor to Professor Muhtar.
Good morning, and thank you so much, Basil, for the kind introduction. Thanks to Debalina for her leadership in this seminar series. Some of you recall that this webinar was supposed to be in San Antonio, so some of the material would be relevant to San Antonio when Debalina mentioned the Texas workshop. What I will be sharing with you is reflections on where the Nexus has been, where the Nexus will go, and we'll talk about some tools, but we'll also talk about some of the applications. So the inspiration for some of the slides that you will see is not only with the Texas boundary, some of it is, but much of it also is drawn from the experiences that we've had over the years globally. So the Nexus has actually found itself as a major element in moving with sustainable development. So some of the discussion that you see is reflected there. I'd like to start with some definitions to see where the Nexus has been. We all know that the water, energy, food as a system, each of these as a system, they're highly interconnected, but they're also vulnerable. The vulnerability comes from that interconnected system that we see. So as you all know that with a drought, you will have water scarcity. You'll also have the vulnerability from food production, depending where that drought hit. But also more importantly, energy sector is a thirsty sector. So a lot of our water resources goes into the energy production and the energy supply that we receive. So this highly interconnected system makes our the global resource security very vulnerable. So this is a framework that we have been working with of the water, energy, food systems or system of systems within a rising economies and the supply chain, with the trade, with the global population pressures and climate change and the governance. So we'll talk a little bit about governance later, but you'll see that complex system that needs a better understanding as we have seen in the silo approach to managing these resources. So that's the framework in which we're gonna be operating. So the approach that we see have some principles that I'd like to highlight some of these principles. The first principle in the Nexus discussion that we have seen is inclusiveness. And inclusiveness has multiple dimensions. So there is an inclusiveness in the sectoral, the water, the energy, the food, and many of us now are expanding horizontally with that, looking at the other dimensions of the Nexus that are actually impacting our resource mobilization, and that's health. That other sectors may be coming in as well. but also looking at the vertical integration of this inclusiveness. So we're looking at the from the ground, people on the ground, people on the policy, people in the private sector, and all of that horizontal and the vertical inclusiveness create a space for dialogue. So the Nexus is not only a place where you identify and quantify these systems, but it's a place for dialogue. And I'll give you some examples of that later. The second principle is the quantitative nature of these interactions. Early in the journey with the Nexus, when conceptually pushed forward that concept, people say, yes, this is great. What do I do with it? How does it help me do better decision making? And I think the key here is the quantification of these interactions that we will see. The third principle is evidence-based. So we need to create legitimacy, we need to create an evidence-based processes, and creating synergy. And we'll have some discussions on synergy later for data generation, for data sharing, and also for solution sharing. Last but not least is to build on current structures and not reinvent the wheel with substitution approach, and build on what we have, what we call the scenarios approach that we have opted to use in this journey. The next few slides are also inspired by our journey for the last several years in San Antonio. We've been working in San Antonio for 6-7 years, and during that journey working with the inclusive discussion and inclusive dialogue, we've learned a few things that I'd like maybe to share some of those with you. Is that the silo or fragmented approach arises from that competition between urban and rural, between different sectors, governance, and inadequate management coordination. So you see many of the management of these primary resources is also governed, but what I'm going to refer to here is a job description. When we deal with this complex system, the governance, which I will have a major stop at that later, but in this case, I'd like to mention here that the governance of these resources has not evolved yet to what we know today about these interconnections and the synergy. So we still are fragmented when it comes to decision making. We still are fragmented when it comes to managing of these resources. The second is how to best allocate water. In this case, we've been working with San Antonio, with the Texas water gap, to meet the needs, calls for synergies and trade-off. This is very important in the discussion of the Nexus, that we need to find these trade-offs. We need to quantify these trade-offs, and we need to work and move the dynamics from competition into synergy. And we'll also have the chance to have some examples. Obstacles also is the lack of negotiation and communication skills. We find ourselves actually in this Nexus discussion that we're not only looking at the science, the engineering, and the quantification and the modeling, we find ourselves in the midst of a lack of negotiation and lack of communication skills that cut across all of these disciplines. So in fact, in an earlier discussion, I would say the next Nexus discussion will have to focus on how to equip the capacity building that we train our students, we train professionals, not only in the Nexus discussion, but in negotiation skills, in communication skills, to allow them to have these synergies transformed into implementable solutions, workable solutions. And at the end of the day, there will be losers and winners in that when we talk about trade-offs. So how do we share the losses? How do we share the wins? And how do we create that communication skills and negotiation skills to move forward with the implementation? So that's the platform we're talking about, and that's the platform that allow us to move from the science to policy making, move the science from developing the tools, analyzing trade-offs, and making sure we communicate these trade-offs and move forward. So the Nexus approach is an important tool in this situation to create that platform for dialogue and facilitate better integration of scientific data and policy consideration. I think we haven't done enough as a Nexus community to work in this space. We may be successful in developing tools. We may be successful in developing data sets that allow for better decision making. But that's not the end of the journey. The end of the journey is to take it all the way to implementation and negotiation and allow for these solutions to be implemented. This slide is actually, I have to admit, the slide is inspired by a lot of conflict in the Middle East region that we spent some time working in that. And how do we use the Nexus to alleviate some of those tensions and impact the regional conflict and allow for the Nexus to become a vehicle for understanding risks and allow for regional integration and allow for the crafting for what I call intelligent policy, intelligent foreign policy. I mean, we can give a lot of examples here. The Nile River Basin is one of those where you've got significant conflict in terms of the upstream and downstream, and that conflict is not getting any better. Not only population growth and demand for more water, but also climate change and the lack of convergence on climate science in whether the Nile River flow is increasing or decreasing, and going into what I call the partitioning or the allocative model has failed us. So in fact, not only in the Nile River Basin, but the Colorado River is another example where that model has failed. The model where we allocate water based on historical data, based on historical demand supply, has failed. We need to look at different models where we look at the what I call that intelligent, synergy-based, efficient production and consumption models that are inspired by the Nexus. So again, when we talk about governance of the Nexus, we have several models that we need to explore, but let me remind us that this is country specific. I think in the past experiences we have in San Antonio, earlier in Qatar, and in other locations, there are no models that fit everybody, that fit every specific country, that fits every specific region. Those are country specific, region specific, and they need to be explored. So in here, I'd like to discuss two different models for managing the Nexus: the centralized model, which may work in some cases, or the distributed model. And I'd like to actually give this even more complexity to this governance model. What happened with the and in fact, I can give you one example from Lebanon, more recently with the mushroom and the renewable energy, specifically the solar energy, going explicitly all over the country because of the lack of the other centralized model. The renewable energy now is having a bloom, a blossom in that. So what does it mean in terms of that, the original centralized model for energy production, and now you've got a more reliable distributed model? How does that evolve? How does the interface between these models evolve? Those discussions need to be brought up to light, and their impact not only on the energy, water, and food security, but their impact on livelihood. All of a sudden, with the distributed models, you have communities that may not have access to energy. Now they do. And I'm referring to rural communities all over the world that now have access to decentralized energy. Now they can produce more food, they can process more food, and they can actually transport that food with cold storage without having it to be spoiled. So we're at the beginning of that revolution, I would say, in the distributed resource space, where we need to make sure that it interfaces well with the existing water, energy, food resources, and how does it interface with the centralized models? And this discussion deserved further exploration. Another example is how does the Nexus governance model, in this case, the energy governance, help us with regional cooperation and regional integration? I'm not sure how many of you are familiar with Desertec. The reason I like to talk about Desertec in this context is an example. I'm not endorsing Desertec or going against it. I think it's a great concept. It failed because of politics. But energy, and just for, by the way, for those of you who are not familiar with Desertec, Desertec is a project that never saw the light, where the idea was to plant solar cells all over North Africa and transport that energy to Europe. It's a great idea where it could have been a win-win. It didn't fly because of politics, but the idea here is for the Nexus to become a catalyst for regional cooperation. In this case, energy, water. In a lot of controversy around the dead dredge, but I'll also provide it here as an example of regional cooperation inspired by the water sector. So you see now that the Nexus now is already becoming a catalyst for these global changes, and the governance need to be looked at. Decentralizing power may serve, have in fact served us very well for many years when it comes to reliability, when it comes to cost, when it comes to efficiency. And how does that interface with regional cooperation? How does that interface with the blooming of the decentralized technologies in many areas? So these issues are and being discussed as we speak, and we need to explore this space even further. So if you look at a bit more in terms of the existing tools and uses of data requirement, I'd like to shed again some thoughts in terms of the what tool we should be using. There are a lot of tools there, and if you want to use one, how would you choose the tool that will be more appropriate? So adopting the Nexus approach to sector management encompasses quantitative and qualitative decision support tools. So I'd like you to highlight that fact, to make sure that highlight that fact. The tool that you'll be addressing has to have at least two of the three: water, energy, food. Two of the three would be, otherwise it would not be a Nexus tool. The second principle is that it should allow for policy analysis. Otherwise, it cannot be used for national and local level decision making. Third, that's my bias, is it has to have an open access. I think there are a lot of open access free tools out there, and endorsing a not open access tool would not be appropriate in my mind at the moment. So again, what we're looking for a tool is to identify and quantify interlinkages of water, energy, food systems. Second is to identify sustainable resource management strategies for governing the water, energy, food nexus. So it's not only the quantification and the identification, it's also looking into strategies. Third is to identify the resource needed for a given scenario. Again, going back to the scenarios. What is meant by that is that what's the land, energy, water footprint for a certain energy portfolio? What's the energy, land, and other environmental footprint for the water scenario? And what is the land, water, energy, and financial requirement for food production? All of these need to be quantified, identified, and allow us to start looking at the comparison, trying to look at the trade-offs, trying to look at pathway forward for these systems to be sustainable. And again, we need, before too long, we need to identify what do we mean by sustainability, and I'll get the chance to do that. And in this, I'd like to introduce the Water, Energy, Food Nexus Tool 2.0, which we've been working with for a while. which allow you to construct scenarios with different sufficiencies of water, sufficiencies of, in this case, food, in terms of their water sources, where that water is coming from, energy sources, country of import. Now, why country of import is important? Because it gives you additional risk factor, which we need to look at. So it may be cheaper to export from a certain country that constitute high risk. However, you may have a little bit higher cost for a country that gives you a lower risk. And that's some of the trade-off that we look at. The tool also allows you to visualize the footprint for that scenario. It allows you, last but not least, to look at the sustainability index. That is our measure of how do we compare various scenarios consistently. Now, I'd like to highlight the sustainability index here in the context of what we're looking for is that a sustainability index for a certain condition or for certain environmental or for certain location may not be the same as compared to other, because it has a compounded factor based on the footprint, but it also has a implication on the policy and in the what we call the weights that the policymaker would put on a certain scenario. An example, I don't think we have time to dwell a lot on this, but this is one of the examples from Morocco that we work on. Morocco has in this case, has 3 different plans: the Green Morocco Plan, the Water Strategy for 2030, and the Morocco Energy for 2030. These 3 plans were not done in a policy coherent way. Okay, so they needed to go through the filter of the analytical tool that we've been developing, and we did all of the analytics, and we did in fact find that there are trade-offs between these 3. So if you want to achieve with the food security, you will, in fact, if you, because the plan calls for reducing cereal, on the expense of increasing water security, land, making land available for other cash crops, and for making more land available for solar energy. For the energy sector, you are making the trade-off between financial implications, because if you invest in all having 42% of the energy coming from solar, you're taking money from other plans that are out there, from the green plan and from the water strategy. And of course, with more solar, you're taking land away from agriculture. So these are the trade-offs that must be looked at before you move forward. And again, there's also trade-off in the water. You gain water security, but because of the lack of investment in the other sectors, you may compromise on the energy security and financial security. So again, the lack of coherence in this case will allow us to identify some of these trade-offs and to move forward with a more intelligent strategy forward. Another example from in our backyard in Texas, where we look at the trade-off analysis in the energy sector, looking at the various oil prices, the natural gas prices, the production of, in this case, the hydraulic fracturing, and the water use. We also looked at the health implication with the trafficability and the added risk in the road safety from the fracking sites. And we were not here trying to provide an answer. We were trying to provide policymaker what we call the sustainability index, which looks into the social, the economic, environmental implication, and allow for the decisions to be made at a holistic level, informed decision moving forward. Key messages, closing with some key messages. There's no size that fits all. We have to look at the local issues, the approach to integrate sustainable management at the local level and allow us to customize the solution. I believe that the human right to access to water, energy, food need to be kept in mind. And this is part of the sustainable development discussion I shared earlier. The approach has to be people-centric and grounded in sustainable development. We need to look at capacity building. And capacity building here is very important. I talked earlier about the lack of coherence and the silo approach and the inability for the Nexus governance to propagate solutions because of the lack of communication, because of the lack of the negotiation skills that allow these solutions that are good for us as a society to be propelled. Again, we did talk about Nexus governance, pros and cons, and last but not least, that the public sector need to be involved and engaged in all of these discussions. I'm not sure if I took more time than my share, and I'd like to stop sharing and give the floor back to Basil. Thank you so much for listening.
Thank you very much for this very interesting presentation. I'm sure there's a lot of questions and a lot of things to think about after this presentation. So please add your questions in the Q&A and we'll go over those at the end of the session. With that, we'll move to our second speaker for today's webinar, Professor Ali Faris, who is an endowed professor at Prairie View A&M University in Texas, where he's chair of the Water Security and Water Energy Food Nexus program. He's currently the editor of the Water Security book series, where he has edited several books, including Climate Change and Extreme Events, Advances in Water Security, Emerging Issues in Groundwater Resources, among many publications in this area. Professor Faris's research interests include disaster preparedness and resiliency, flood prediction and mitigation, water security, water energy food nexus, watershed hydrology and management, water allocation, irrigation management, and others, including adaptation and mitigation of climate variability. Dr. Faris, we're looking forward to your to sharing your case studies and your work on the water energy food nexus space, and the floor is yours.
Thank you, Basil, and hello, everybody. Howdy, as we say it here in Texas. It's my pleasure to talk to you today and to join my colleagues, Professor Rabia Mahtar and Basil and Dr. Basil and Dr. Davelina also. So I'm going to talk today about the water, energy, food nexus and climate change. I'm going to go through a couple of case studies that we have been doing here at Prairie View A&M University on the linkages between food, water, energy, and food, and also climate change as well. So I would like to recognize my colleague, Rapendra Awal, who shared with me this work that we have been doing together as a team. So if my slides can collaborate with me. So the first case study will be about optimum turf grass irrigation requirement and corresponding water energy CO2 nexus across Harris County, Texas. And the second one, I'm going to talk about climate change induced variation in blue and green water usage in US urban agriculture. As we all know, the world is getting more and more urbanized and less rural. The red here shows the rate of increase of the population in urban area is going to surpass 6 billion people. However, that increase in population in urban area is accompanied by a decrease of rural area residents. So with that comes the need for more food, for more water resources, and also for more energy and in these urban areas. For this case, for these two case studies, we use a modeling approach. In this one, we are using an irrigation water management system called IMNSS. This is a numerical simulation model that combines water balance approach with site-specific, also crop-specific data to calculate a water budget. IMNSS is the grandfather or the father of IWRITS, which is a water allocation model that has been used in the state of Hawaii that I developed for them. to determine water allocation for different water users across the state of Hawaii. So the model uses a very simplistic approach, basically the input into the system and output from the system, and calculates how much irrigation do we need based on historical weather, daily weather data. So it uses evapotranspiration, precipitation, interception by the plant canopy, evaporation, runoff, drainage below the root zone, and also accounts for groundwater contribution if you have a high water table. So the input for the model climate parameters, as discussed here, reference evapotranspiration, soil data, water holding capacity, and soil layers, depth, etc. Crop data will be crop coefficient, rooting depth, and other parameters. So for this, for the case one, where we worked on determining optimum turf grass irrigation requirement and corresponding water energy CO2 nexus across Harris County, Texas. Harris County is where Houston is. Houston is the fourth and soon to be the third largest city in the US with over 4 million people. And if you account the metropolitan area of Houston, and we call it Houston-Galveston area, we have about more than 6 million people living in this area. So this is a very urbanized area, so there is lots of demand for water to irrigate turf. So Harris County, as you see in here on the map, it is the Harris County. So the objective of these of this first study is to calculate site-specific optimum irrigation requirement for turf grass. If we would like to maintain adequate water resources for the county, we need to optimize water irrigation requirement for turf grass. The second is to estimate water and energy savings and reduction in CO2 emission if optimum turf grass irrigation is adapted. So this is a very teaching moment for people to show them that if you do save 1 inch, 2 inches, whatever the amount you save in water irrigation, how much water you would save, but at the same time, how much energy you would save from not wasting, and more importantly, also how much CO2 you would not to emit if you practice optimum irrigation requirement. So we ran the model for 48 locations. These are the locations where we ran the model there using historical data, 42 years of data. And then we calculate, we're going to report to you later on the results from point 1, which is the driest point here in the county, because there is a rainfall gradient, as you will see. Rain is less here and increases as you go southeasterly toward the other edge of the county. So this location has more rain, less evapotranspiration, and this location has a higher evapotranspiration but less water. We're talking about a variation of rainfall between 0.1 and 0.2, about 20%. So there is 20% more rain here than it is here. And the evapotranspiration is here is 10% less on that one. So there is the gradient here. Rainfall increases as you go this way. The evapotranspiration increases as you go the other way. So keeping that in mind, okay, this is the map of Harris County. This is the rainfall map. As you can see, as I mentioned earlier, we have about 1,400 millimeters of rain here in this part of the southeast. This is the Gulf of Mexico here. So this is the southeast of the county. And you have about 1,140 millimeters here. So you have about 20% rainfall difference between these two locations and counties. So there's a strong spatiotemporal variability of the rain across the county. The same thing for the ET. The ET is higher here and lower here. There is a 10% increase of evapotranspiration if you go from wet area to the drier, relatively drier area of the county. This is the land use map of the county. So you can see the red is urbanized area, and you can see the other areas where you can find the pasture and etc., like the yellow one. So this is where Houston downtown here. So you can see it's very urbanized, and as you go a little bit further, so Chris, this is closer to Waller County where we sit here. We are near Waller County and Harris County. It's less urbanized, but in general, Harris County is a very urbanized area. So the modeling approach or the modeling framework we use, we have the irrigation water management model here as we discussed. This model requires input, crop data, requires soil input, soil data. We use curve number to determine the runoff, leaf area index to determine the canopy intersections, and water holding capacity here from the soil data. And we have the evapotranspiration data, the weather data, and the rainfall data. We use this database that we have that has data for over 40 years for Harris County. So all this information is fed to the model, and then the model determines irrigation water requirements. Based on this information, it tells you, it uses those historical data and basically grows your crop across using those historical data, and determine if you were to use optimum irrigation for that crop, or using that historical data, how much irrigation you would require. And then it feeds it here, and then we can give us output. So increase in average irrigation water requirement will subsequent increase in water requirement and increase in energy requirement, and then increase in CO2 emission, because more energy production or uses more CO2 production. So the results of this analysis, remember we said this is the wet, driest part and have higher evapotranspiration. This is the lowest in evapotranspiration, but wettest. So the gradient goes this way, if you recall from one. So this is 0.1, 4, 3, and 2. So these are the results, any of the average results here. For 0.1, you see the irrigation requirement here is in red. The rainfall is in purple, and you have the evapotranspiration in blue. So you see, if you focus on the rainfall, you will see that gross rainfall is lower here in this point and increases, slightly increases as you go to the southeast part of the county. The opposite is for the evapotranspiration. Crop evapotranspiration is higher here, it decreases slightly, decreases. Remember, there is a 10% decrease in evapotranspiration, but there is an increase of 20% in the rainfall, as you have seen it from the purple data. So this would translate in irrigation requirement here in red. So you have, for this location, you need 919 millimeters of irrigation. But if you go a little bit wetter, you only have 868. A little wetter, you have 764, 703 millimeters as you go here. So there is a difference between here. You can go from here to here. There is about 215 millimeters of rain difference between here and there. So there is about more than 22 or 23% decreases in irrigation requirement as go here. So it will be a waste of energy and water and resources to irrigate the crops here the same way as we do there. So that's why we need a spatial temporal allocation of water. So this is in general for the annual one or the average. On the monthly basis, you can see there is a similarity. Still the same trend is there, but you do have, and this is basically only irrigation requirements for these 4 points. So always these have higher irrigation, and this number 4 has lower irrigation requirements. But overall, from January, we have less requirement. June, May, during the summer, spring and summer and fall time, you have high irrigation demand and then decreases. Okay, so based on this study, we took the example saying incremental increases in annual irrigation requirement and corresponding water volume, energy, and food next. So imagine if the optimum turf grass requirement is 783 millimeters per year. So if we irrigate 1 inch more or 2 inches more, etc., what would be the average water requirements? This is the city that needs to provide for the crop. Increased volume. So compared to this one, there's a 10 million cubic meter increase compared to the optimum, and up to 52 here. And the same thing for groundwater, because the water that is supplied to the city, some of it is 33% of it is groundwater, 66% of it or 67% is from surface water. And the energy needed for surface and groundwater is different. So this is the total energy for that water needed. And this is the CO2 emission corresponding to that one. So if the annual irrigation requirement used is higher than the optimum requirement by just 1 inch, which is 25.4 millimeters, then the annual irrigation water loss will be about, across the county, will be almost 10.5 million cubic meter, which is equivalent to the annual water use of 30,561 single family houses, which is corresponding to excess energy use and CO2 emission will be by 444,433 megawatt hour, and emission of unnecessary emission of 2,590 metric tons of CO2. So this is just when we over irrigate by 1 inch, these are the consequences. So we are depriving almost 30,000 or 31,000 single home family from water uses. We are wasting this time how much energy, and we are producing unnecessary metric tons. So as you can see from this example, this can be a great tool to teach people about water saving, energy saving, and climate change and the interconnectedness between the two. The second case study, which is a climate change induced variation in blue and green water usage in the US urban agriculture. This is the second study led by 2 PhD students from University of Texas that worked with me and Prendra on this as part of their summer program. So the objective is we are going to check the variation in blue water and green water usage in US urban agriculture. As you know, blue water, we know from the definition, simple definition of blue water is water coming from groundwater or surface water, and the green water is water coming from our rainfall. So of course, we would like to optimize the water that is coming from our from rain. We can use it for agriculture. That's one of the way of saving water. So for this case, the objectives of this study was to examine 8 mid-sized cities across the US to assess how climate change might impact the medium-term irrigation requirement of urban farms. And the second objective is to assess how these changes in irrigation requirement will impact energy and greenhouse gas emission of urban agriculture. So we used, again, I meant CIS, but we fed it climate data for current data and for projected for the mid-century data, weather data. And both of them, we fed them to the model, and the model gave us the budget of historical or water requirement of these crops and the future water budget for crops in the future by 2050. So again, the same thing, using this RCP5 for climate change scenario. We focus on this particular scenario. So the cities that we use in our studies were, as you can see, distributed across the US, from San Jose, California, to San Diego, California, to Buffalo, New York, to Austin, Texas, etc. So these cities, they have different, as you can see here, the rain and temperature. They have from wet like Buffalo to dry like San Diego. So lots of variability, climatic and edaphic and so on, to North Carolina, Raleigh, North Carolina, etc. So for these locations, we selected crops. We selected 3 crops in addition to turf grass. So we selected carrots, sweet corn, and spinach. So these are the growing seasons. So you can see there is a variability in the growing season across the states, but most of the growing season basically runs from March or late February to June, July. So that's basically most of the growth. This is the crop coefficient for the different crops, for the spinach in red, for the carrot in purple, and for the sweet corn in green. The climatic regime, climate data for the different cities. As you can see, there is a lot of course, Jacksonville, Florida has more rain compared to San Jose, California, and so on. So we will see what would be the results of this analysis. Turf grass requirement. So we can see here the turf grass requirement here, baseline is in purple. For future irrigation requirement, baseline and ET here, and future evapotranspiration and groundwater gross irrigation requirement. Okay, so you can see for the west of the U.S., the central of the U.S., and the eastern of the U.S. We calculate the changes in turf grass irrigation requirement ranges from negative 46 to negative 183. So in the future, there is experience that most changes have both substantial change in temperature and precipitation, regional differences in plant types and corresponding crop parameters may have real implication at the scale. So crop irrigation requirements, changes in irrigation requirement varies from negative 62. So there is a decrease in irrigation requirement in some locations, and there is an increase of almost doubling, more than doubling of the irrigation in some locations across the U.S. Water balance again highlights relationship and importance of evapotranspiration precipitation as the 2 major driving force of this water requirements or water usage. Okay, so carrot irrigation requirement, current irrigation requirement here, as you can see, for example, here, future irrigation requirement. Okay, for carrot in Jacksonville, there is a decrease. There will be decrease. For Kansas City, almost there is no difference between the current and the future one. For Portland, Oregon, there is a completely lots of increase in water requirement in the future compared to the current, and that's due to changes in the climate, declining evapotranspiration and rainfall, etc. Similar, I mean, there are some results that are Salt Lake City, it's a drier environment, but Raleigh, North Carolina, for example, you almost can grow carrot with a little rainfall with, as you compare the rainfall requirement, irrigation requirement here in Raleigh, North Carolina to Portland, there is a big difference in irrigation requirement. So technically, you can irrigate, you can grow carrot, North Carolina, Raleigh, North Carolina, with almost good, entirely with green water. But for Portland, you need lots of blue water here because of that irrigation requirement. So the irrigation requirement here represents basically your blue water. Okay, so like San Jose here, it's better, much better than Portland, Oregon. So greenhouse gases emission, you can see here Western United States, lots of irrigation, lots of CO2 emissions because they require lots of irrigation. However, central and eastern United States, where it is most wet, you have less CO2 emission for the same crop because you have more water, because you have so green water contribution, is substantial here. Now, up to 90% of the water used by the crop is coming from green water contribution, and the eastern United States compared to western United States. So there is the green water contribution, there is the energy requirement, and they go hand in hand. So if you the green water contribution is higher, less energy requirement. If you have less green water requirement, then you have contribution, you have higher energy requirements. So comparison of crops, turf grass, sweet corn, carrot, spinach. Turf grass, you have almost increase in the water requirement. Sweet corn, you have some increase, but in some locations you have decrease. Carrot has some decreases in some locations in the future compared to the current one. And spinach has some mixing results. In summary, irrigation requirement decreases from its highest level in the northwest of the country to its lowest level in the southeast corner of the country. County, I'm sorry, this is for the first study, mainly in response to combined effect of rainfall and reference, importance of considering spatial temporary climate change when considering adaptation of mitigation strategies. I think with that, I would like to thank you, and I will be happy to entertain any of your questions if you have any. Thank you.
Thank you very much, Dr. Ali, for sharing your case studies from Texas, Houston, and from different national case studies as well. I see there's a lot of engagement in our Q&A section, so please keep your questions coming. I've been seeing a lot of activity there, and again, we're going to go over some of these questions with the remaining time following our third presentation. With that, we'll move to Dr. Debelina Sengupta, who's the Coastal Resilience Program Director for Texas Sea Grant at Texas A&M University, where she also has a courtesy appointment as a fellow at the Institute of Science, Technology, and Public Policy, as well as a graduate faculty at the R.T. McFerrin Department of Chemical Engineering. As Coastal Resilient Program Director, Debelina plans, organizes, directs, and manages extension activities associated with resilient communities and economies strategic focus area. She aims to work collaboratively to implement more resilient and sustainability strategies in coastal communities, and has authored 2 books, one on chemicals and from biomass and measuring progress towards sustainability, which I believe we're going to hear more about today. With that, I'll give you the floor, Debelina.
Thank you very much, Basil, and thank you to all the speakers who spoke before me. It's an honor to share the stage with Dr. Rabia Mokhtar and Dr. Ali Fares. So this project, the Direfuse project, is very close to my heart, because what we have tried to do this with the team is look at the disaster perspectives and tie those into our food, energy, water system. So what are the specific disaster conditions that lead to our food, energy, water system disruptions? And that's where our uniqueness comes in this project and future directions. So again, as Basil had mentioned, this is a planning grant phase. So we are trying to inform you about our team through the capabilities and capacity that we have. And that's where we are working together. So a lot of the research that I'm going to present today had been done in my previous role as Associate Director of the Gas and Fuels Research Center. And after some time, the boundaries for convergence research purposes, the boundaries of when and where research was done becomes blurred. So I'm going to walk you through a few systems analysis methods and tools that we have used. So sustainability in itself is a complex topic, as Rabia and Ali has highlighted in some of the work that they have shared. I look at it from an engineer's perspective, and being a chemical engineer, the questions that come to my mind in some aspects, like what does sustainability mean actually? And that's where I ask this to my class of students sometimes, that does it mean just riding a bike? Does it mean moving to a solar powered process? Does it mean using electric hybrid cars? But what does it mean? So it is a complex topic. It has several interpretations, actors, and stakeholders that Rabia has so much mentioned in his discussions. So the focus of today's work, and for my part, is what are the tools available to solve sustainability challenges in the food, energy, water systems. So Rabia mentioned the Sustainable Development Goals. This is a recap of the 17 goals that we have. And if you look at the Sustainable Development Goals, those are at the global level, these goals exist for the different countries that take part in this attaining these goals. So there are 17 goals, 169 targets. And the way I see it, these targets are the ways in which we can target our work towards reaching these goals. When I say we, I talk about my role as an engineer, as a process engineer, as a chemical engineer, or a systems engineer, or in engineering in general. We have a unique opportunity to provide the sound science, quantification, analytical methods, and engineering solutions. However, for convergence of the solutions, and I mentioned convergence, Basil is an expert in convergence research, we have discussed so much that there is a very critical need where we need to work with social, environmental, and technological experts together, and using some of the systems engineering principles. And one thing that Rabia mentioned very closely is that we have to have a combination of quantitative combined with qualitative solutions, because that is where we struggle the most in informing, in negotiating with these scientific solutions to bring it into the social perspectives and bringing those qualitative decision-making using these scientific solutions. So that's where we have to provide a link for bridging this. So very briefly, I'll go over some of the concepts and methods that I have been personally involved in developing, and that can be applicable to food, energy, water nexus. One of the methods that I had the privilege of developing at the United States Environmental Protection Agency was a method called sustainability footprint, where we have lots of metrics, methods, indicators, but if there is a quantitative indicator that we can have, we developed a method to use those indicators to make a single aggregate indicator called the sustainability footprint that we call DE. And then using that footprint indicator, we can make decisions regarding the indicators that we are actually using, whether they are useful in measuring progress, whether we collect lots of data, but whether that data collection is at all necessary. And we have used this indicator method for understanding environmental sustainability of countries using the UN MDG indicators. For those of you who are not aware of MDG was the Millennium Development Goals, which were then replaced very recently with the Sustainable Development Goals. But the UN MDG indicators were studied for the environmental sustainability part, if you were aware of those indicators. We studied a set of countries, OECD and non-OECD countries, and ranked those countries based on the indicators and their order of importance of the indicators. We have also used this method to study process systems, such as doing a case study for methanol from carbon dioxide. We also used this for doing auto shredder residues. So I just want to mention that this is a very powerful tool that can be used for multiple indicators and multiple systems, as long as you are able to define the system and have numerical indicators. Now, one of the major challenges that we had faced here was that the indicators themselves were sometimes very qualitative indicators, like yes, no type of indicators. And that's where this tool has to be used in tandem with the quantitative and those qualitative indicators, with the quantitative indicators being studied in this method, but the qualitative indicators to be put in as weight factors. A very critical piece of this, the systems view. I mentioned systems, and these indicators need to have a systems understanding. So this is an overall picture of the systems view that we've borrowed from Joseph Fixel from Ohio State University. He's a great name in resilience theories. So we looked at economy, society, and environment as three different pillars of capitals, and look at the interactions of these systems with each other. Also, with systems comes a question of scale. So we proposed the scale of systems for sustainability considerations. We started with 4 different scales, and later on we have also expanded the type 2 into 2 different scales. So we have now in our book, we have put in 5 different types of scales. So there are different types of indicators that you use at type 1, and a type 1, a global scale indicator, will be very different from a type 4 sustainable technologies level indicator. So understanding the type of the scale that you're working with, and Ali gave a very good example of the scale of the Houston area, the Harris County area, that would fall under a type 2 system, which is bounded by a geographical boundary. Then there are business systems that are that may work across different geographical boundaries. But the takeaway here is that how do we link the information needed at global scales to what is in our control? For example, I, as a chemical engineer, probably will never be able to work with the policymakers at the global scale, but I have in my control the plant system boundaries to work with, and what goes out of my plant system is what is in our control. So if we can devise and design new types of technologies that will be less polluting, less impactful, then that is a contribution that we can really have towards sustainability. So from this, we developed some axioms in sustainability. It is about systems, and it is always relative. It is never absolute. And sustainability functions are described by a parsimonious set of indicators. So you cannot work with an infinite set of indicators because that's impossible to work with. But the scale of the system determines the nature and the set of indicators and the sustainability analysis that you need to do. So now coming to food, energy, water systems, we see that food, energy, water is an approach to that started with food security and sustainable agriculture, but the interactions that we see in the food, energy, and water systems are so intricate, and I wholeheartedly support the different complexities that Rabia has so much highlighted. The complexity of these systems is so difficult to handle. So sometimes I feel like it's like one of those thorn balls that you don't know where you want to start with, because you are going to be pricked by it. But that nexus, the way we look at it, can be studied from any one of the pivots of food, energy, or water systems. And then, as Rabia mentioned, at least 2 of the nodes need to be studied and the interactions between those. And for us, we need to have a study of this with the convergence approach for technical knowledge interacting with the social sciences. So that's where, again, I mentioned the food node, energy, and water node, and then we can start from any node and study the interactions. And the methods that currently exist start from very simple to very complex. And again, as it depends on the type of system that we study. But any analytical method needs to have a discussion on the boundaries, the interactions within and outside the boundaries, the optimization. And by optimization, I do not mean necessarily arriving at a maxima or a minima, because that is opposite to the optimization concept. So we may have a maxima or minima determined by mathematical optimization, but combining it with the social policies, we can come to an optimum that's acceptable to all. And then we use modeling and other methods. And layered on this is the critical need for the governance piece. So I'll very briefly touch upon water nexus challenges from water systems node and energy systems node. So this is a systems approach to water management, where we have, as I mentioned, the type 1 global scale, where we can look at the water cycle at the global scale. And then from the scale, we have groundwater, we have surface water, we have precipitation, condensation, evaporation, and all of the different water systems that run. So from this water system, so we use this model to write a paper on incorporating systems thinking in engineering design. So taking from this water system, we have a riverine system, let's say, that runs from the mountains. And then from that riverine system, it's a surface water system. We have draws into public supply, rural and domestic livestock, power generation and industrial use, and farmland and irrigation. When it comes to this riverine system, that system is bounded by the geographical boundaries, and that's where a lot of the conflicts come in the access to that water. So, and this is typically managed by local authorities and individual entities. So what happens upstream of that river very much affects what goes downstream in that river. And as Coastal Resilience Program Director, I have firsthand experience working with some of these communities where the Baffin Bay area, let's say south of Corpus Christi, is being impacted by the inputs to the rivers that flow into the Baffin Bay, such as the San Fernando and Petronila Creek, and how that impacts the water system. So it is bounded by geographical boundaries and has this. Now, the method that we use to study the system is called an interception or interception method. So in chemical engineering, let's say we have physical and chemical processes that I've used an example of an industrial process system that is drawing water into that industry from the river. And a lot of industries have developed along the rivers because of this access to water. And that's where the physical and chemical processes that prepare the water for use and from use, that is the inlet and discharge into the natural water systems, is a very critical method that allows us to understand the water energy nexus that happens in these areas. So industrial ecology is a sustainability method that has been in place for quite a number of years. And that's where we propose the methodology for study as industrial ecology. And using this, going back to the San Antonio case study, we developed a industrial source interceptor, water source interceptor sink diagram, where we looked at all the possible resources for water in the region, and we looked at the different uses. And then once that water has been used, because of water scarcity, we were looking at how can we reuse that water and where would that go? So the interceptor model here, the water interceptor network, is a theoretical model that would allow us to study the different trade-offs that can happen and which type of water and the quality. So one of the major issues here is the total quantity of water is definitely an interesting parameters to study, but the quality of the water at the inlet and primarily outlet quality that depends on the type of processes is very important for us to study. And so necessary for sustainability of local and regional water quality for health, safety, and economic development. And on top of it, you have to understand that each of the water treatment options comes with an energy footprint. And so energy requirement for these processes that support water treatment are utilities that require operating costs. And the minimization of purchased utilities can be achieved by integrating with excess process energy that is currently wasted. So these are certain areas that we studied in this paper. And so taking this to an international location, we try to apply this to Haldia area, and we're still working on it on existing industries. So Haldia is an industrial region in India, and that also is fed by rivers, as you see along the coast right here. And there are multiple industries that exist, like the port exists, then there are battery manufacturing industries, there are different petrochemicals and petroleum and refineries. So it is an industrial zone that can be utilize this method, and we are working with the Bengal Chamber of Commerce and Industry in the region to define this and then use that source interceptor sink model to see how the water quality can be improved in this region. And this is an example of how we have plants in the region, and we have wastes, and we have fresh resources, and we can propose a centralized mixing and interception system in that region. So going to that example, industrial investment is needed for pretreatment, investment for discharge control, requires energy for water pretreatment, and meet government imposed regulations. And the reason why this is very important is that it demonstrates corporate social responsibility for the near vicinity as well as downstream of that region. It shows minimal impact on environment and take advantage of existing industries in a region with low-grade energy recovery, and thereby maximizing or profit or minimize cost to energy use, cleanup, and future potential litigation. Another example is of a paper pulping process, and I will very quickly run through this for interest of time. We have the method used for looking at the moisture that comes in with the paper pulping process and the water that goes out. So there you can see there is a lot of excess water, and if we were to use fresh water for this entire process, we would be using a significant amount of water. So we used our methods of process integration to look at the amount that can be recovered as an interceptor of the water model. And we have that recycled. So we were able to recycle about 11,000 gallons of water, reducing the freshwater target. And then there are different methods of interception. So depending on what the freshwater target is, a direct recycle, a single interception, or new technology can be used. So we can quantify the amount that we can get back. Now, going to the Nexus challenge of this type of source interceptor sink and the Nexus challenges that this models can address is the energy requirements for water treatment, the water demand increase for an increased energy production, water reuse quality requirements for energy use, and water food nexus challenges is that water resource distribution for various purposes, including agriculture, food insecurity due to water scarcity, and disaster conditions for drought, flooding, saline water intrusion. We can address some of those challenges through this type of modeling. Now, I don't have much time, so I'll just walk through the Nexus challenges from energy systems. This is our US energy consumption in 2019. We have electricity generation, we have residential, commercial, industrial, and transportation, and the entire energy resources that are used to generate this. Now, the percentages that you see here is the amount of waste energy that is generated from these processes. So there is a significant opportunity to reduce rejected energy, thereby bringing in a energy efficiency. But very intricately connected to this energy is in the electricity generation, where it comes with a water footprint. So if we are able to look at water energy nexus, that would be great. Now, the energy production and consumption in the US is expected to rise, and a lot of the expected increases to come from the natural gas. So natural gas is considered as a transition energy, and you see that shale gas is one of the major, especially in Texas and Pennsylvania, this is a major source of projected energy increase. This is a shale gas supply chain that you can see where we have fracking, and that is the part that I'm going to focus on. Fracking is a water intensive process, so there is a very strong need for energy water nexus using the fracking. And right now, as we speak in West Texas, they're thinking of utilizing this fracking water that's used for fracking and comes back as produced or formation water to be recycled and reused for certain irrigation purposes or agricultural purposes in West Texas and the dry areas. So we have worked on Rapid Manufacturing Institute project on treating shale gas wastewater and looking at the energy and water nexus in that space. So we have looked at the desalination processes. We have looked at the gas monetization, which I'm not going to go over. We have looked at carbon capture and utilization space in the natural gas space. And there we have found some very interesting solutions. But also looking at future energy of biomass. Biomass is, it showed up on Rabia's slide, like biofuels is a very critical area where food, energy, and water nexus issues come in, and we have a strong base in the biomass use as energy feedstock, and there irrigation plays a great role, and water energy nexus comes into play. Basil also mentioned the chemicals from biomass, so if we were to replace chemicals, that's another area. And finally, the case study that I'm going to mention is the sustainable supply chain design for biofuels. So we have looked at the emissions and water use from biofuels that have formed the core of the EPA's regulations for biofuel mandates in the United States. So in conclusion, I would say that some of the nexus challenges that would exist here, energy water nexus, is water requirements for increased bioenergy production, water requirements for shale gas production, and water loss in energy production. And some of the energy food nexus challenges that exist are land use for food crops versus energy crop, urban farming using innovative energy resource utilization, and reduction in energy use for fertilizers. With that, I would like to thank you all, and thanks, Basil, for this wonderful hosting.
Thank you very much, Dabelina, and thank you to all our speakers. Again, these are really interesting presentations with very different conceptualizations and examples and case studies that offer lessons learned that we could build on. I've been monitoring the Q&A section, and it's really fascinating to see the diversity of topics that are being covered, from governance to dryland agriculture to biodiversity to data intensive approaches and the need to translate science and policy. I'd like to ask you each maybe a quick question. So a lot of the questions that I saw came after Dr. Muhtar's presentation. Would you like to comment on any of the specific questions you answered? Again, there were several on dry land agriculture and the importance of taking a Nexus approach, the importance of taking a Nexus governance approach, as well as translating science of policy.
Thank you, Basil. Yes, there was several, and I'm really thankful for the audience who have been awake and challenging us this morning. There was an insightful comment about the rain-fed agriculture. Just as a frame of reference for all of you out there, rain-fed agriculture is responsible for 2/3 of our food supply. So it's not a minor issue, it's a major issue. And a big effort as we speak is on quantifying green water, trying to optimize green water space. And I think the green water offers one of the most exciting opportunities to wean blue water from the food production. And if we're successful, I think this would be a huge implication, not only from a food security perspective, but also to release water from fresh water, makes it available for other sectors. It has less emission and less energy use. So that's an area I think is an excellent area that needs to be looked at. A lot of other questions related to capacity building and negotiation skills. We need more of that. I don't think any one of us is, at least I wasn't prepared that when we ventured into the Nexus that people are going to be happy for solution and people are going to be angry for the solution. So how do you manage that in a system solution? I think this is something important. And the ecosystem as a major stakeholder also came strong, and then I think needs to be mindful. And the governance issue came back with I don't think we have explored the space of governance yet to the fullest. So we need to be mindful of the what would be the appropriate governance moving forward. The one thing that I'd like to leave us here with is that the Nexus is a useful platform. It allows to quantify some of these risks, but I think we are at the beginning of that journey. The Nexus is less than 17 years old discipline, and there's a lot of questions that need to be answered.
Absolutely, thank you very much. One specific question we also had for Dr. Faris following his presentation. Did you just answer that question? Because
I tried. I clicked on the answer, but I missed it. But the answer
no,
would
I
be,
can't see the question anymore. So did you have an answer?
Yeah, he must have clicked on the answer on the fly. So
answer live. That's what it says.
Verbally. Go ahead.
Well, the question was about the evapotranspiration. Was it for St. Augustine grass or? Well, for the southern regions, like Jacksonville, Florida, or we used what we call them warm type of grasses, like St. Augustine or Bermuda grass is the type of grass we use for. However, for northern climate like Buffalo and others, where we used cool season grass like Kentucky bluegrass and other grasses that really have a different water requirement than the warm season grass in the southern part of the location. So the answer, we used both, not for the summer, for the area that are warmer, like as I mentioned, Jacksonville, we use those warmer grass type, but for the areas that are northern, we use the cool season grass.
Thank you, Dr. Ali. I also see a question for Dr. Sengupta following your presentation as well, coming from Johnny. who's asking about the nature of the challenges that we face today, which have emergent properties and are problem-oriented. So I think he's referring to the sustainability quantitative indicators that you mentioned, and he's asking about how do these account for the complex interacting system components that contribute to emergent properties.
So I would say that I am probably an expert in analysis of indicators, but the indicators themselves, what we typically try to use are the ones that are defined by either the United Nations or certain indicators that your community, like it may be my local community leader who has determined that my indicators of importance are water quality, water availability, energy security, energy availability in my region. So we will work with those indicators and then analyze based on that and see how those are. So there is that interesting challenge is like we can start from a master set of indicators and reduce that set of indicators for a model reduction. Or if you have your community define your value system based on your value system, if you value your water, which is supposed to be having a value. So we can assist with the master set of indicators that you can choose, but at least like have a starting point from your community. And so we worked with the United Nations defined indicators or process systems based indicators, but that's where the complexities are, I assume, to some extent taken into account by the decision makers.
Thank you very much, Davelina. Definitely fascinating discussion and a lot of
Basil,
insights and
if I
lessons.
may,
Yes.
there was one issue that I'd like to highlight on something about national security. When I'll give an example. When Qatar, for example, was under a blockade, they could not bring in food into the country. Everything else becomes okay if you use more water, more energy, more land, more emissions, higher cost, because you need to feed your people. So I think there are issues when it comes to what I'm gonna label national security. Then the resource nexus becomes a way to assess the least painful approach to moving forward. So that dynamics, I'm seeing that in the chat, that dynamics is very important. So we're only promoting a science-based policy making. However, decision makers, for whatever reason, they may choose to not necessarily choose the most sustainable route forward for national security concerns. And I think, I mean, that's the becomes a wicked issue, is what's our role in science? If at any point in the game, a policymaker would raise that flag, say, you know what, we're under threat, we're under, this is unprecedented circumstances, so they make their own choice. That's a very wicked discussion problem that I don't know how to proceed with, but I just wanted to highlight that.
Thank you very much. And again, it was a fascinating discussion, and thank you for our audience for being very active and engaging with our speakers for today. Thank you for joining. I think we're reaching the end of our session today. A recording will be available online on the project website, so look out for that. And thank you very much, and see you on future webinars.
Thank you very much.
Thank you.
Thank you, Dr. Fares, and thank you, Dr. Mohtar, for your time.
You're welcome. Thank you for our audience.
Was a lot of fun. Thank you.
I hope everything went well.
Thank you.
It went very well. Okay. When will the recording be uploaded?